Okay, good. I guess all of you can see. Let's kick it off. So our first experiment today is on transverse waves. Okay, trying to understand the phenomenon of transverse waves. And here you have a transverse wave setup. Yeah, these are the controls. So this is the reset control over here. This is the parameters control for the transverse wave. And this is the particles. Yeah, so you've got particles P and Q, which are specific particles, and this point W is actually just a wave front point. So what I'm going to do is these are our three sets of controls that we have. So remember that when we do transverse waves, there are really two graphs, yeah, at any point in time. The left-hand side graph represents all the particles at any point. So all the particles originally lie on this black line. Okay, so this is like a distance. All right, on the x-axis. On the y-axis is the vertical displacement of each of the particles. On the right-hand side graph, on the x-axis you have time. And on the y-axis you've got displacement of just this particle P. Okay, only P. So on the left hand side we're tracking all particles, on the right hand side we're tracking only what happens to P over time. Okay, those are the two graphs. This red line here in the left hand side graph represents the positions of all the particles. Okay, not just P and Q. We've chosen to highlight P and Q, but really it represents all the particles. Alright, and because there are too many, we can't really show too many. We are really only showing two particles, but you should know that there are plenty. So I'm going to set the wavelength parameter, this lambda parameter, to 4. Okay, so that it becomes reasonably easy to look at one wave. I'm going to set this frequency parameter to 10. Right? And then finally I'm going to set the amplitude parameter at 2. I'm now going to use the position control, and I'm going to set P so that it coincides with 0.4, yeah, 0.4 on this graph over here. So here we go, 0.4. You should be able to chat with me, yeah, using this on the top of your, you should see the green box and you should see a chat button. You should be able to chat with me here. I'm sending you a message. Can you just confirm? Rest of you, can you all confirm you can see? So we'll use this chat box instead of the one on, instead of using the one on the classroom. Okay, so it's just easier. You don't have to switch tabs. So now what I'm going to do is, like I said, I'm moving P so that it coincides with the 0.4, right? So as you can see, as I move it, exactly at 0.4. I'm going to now move Q so that it coincides with 0.5, yeah, so somewhere in the middle. Okay, that's the position of particle Q. As you can see, it's at 5, particle P is at 0.4. Yes, can you see this? Rest of you, can you see this? Okay, let's move on. So now what I'm going to do, and I'm going to set this particle W so that it coincides with a trough. It's not a particle, it's just a point on the wave. Okay, so it's right at the bottom. Those are my initial settings. Now look at this side graph first. Okay, and focus on point P. Alright, look on the right side. You can see that the displacement of point P from the horizontal black line, which is their starting position, is 0, and therefore on the right side also you can see that the displacement on the y-axis at time t equal to 0 is 0. Can you see this? Okay, so now when I press start, what's going to happen is on the left hand side, we're going to see how particles P and Q move, and how the wavefront itself moves. On the right hand side, what we're going to see is what's going to happen just to particle P over time. Okay, that's what we're going to see. So let me start now and observe what happens. Okay, let me just stop it here. Did you see that? Did you see how the particles move up and down and the wave moves forward? And then on the right hand side, did you see the motion of the particle over time? Yeah, so this particle P, its displacement goes down first, then goes up, and then goes down again. So this particle is really, it's vibrating in one place, up and down, but this is time on this axis. And that's why these two graphs, although they look the same, yeah, so when we've done these two graphs in class, there could have been this confusion that both these are actually the same. They're not the same, they're two separate graphs. The left hand side graph is a distance on the x-axis, a distance on the y-axis. The right hand side graph is time on the x-axis and displacement on the y-axis. Is this clear? Okay, very good. So let's move on. Now, let's make the following let's focus on the left hand side and let's make the following observations with respect to a transverse wave. The first observation is both P and Q move up and down. They do not move sideways. Okay, look at this wave front. It was somewhere here to start with, but the wave front itself has moved here. But P and Q have stayed in their original places. P is still at 4, Q is still at 5. Okay, so in a transverse wave, you have particles moving up and down. This is the first observation. Okay. Second observation is that the motion of Q kind of lags the motion of particle P by just a little bit. Let me start this again and you can please observe. So it's just a little bit behind P in terms of its motion. Yeah? You should be able to see that. And that's really what causes the wave to appear to move to the right, because if, let's say, P represented a crest, then a few seconds later Q will represent the crest. So it seems like it's moved from here to here. And that's why it seems like the wave is moving, whereas the particles are actually only moving up and down, but it seems like the wave is moving left to right. Is this clear? Okay, let me start it again and please take a look at the velocity of particle, let's say P or Q. Okay, see where it's maximum, see where it's minimum. Okay, I've paused it again. Do we agree that the velocity seems to be the maximum when its displacement is 0, which means right at the center? Rest of you, yes? Do we agree? And do we agree that its velocity is 0 at the crest and trough points, at the highest and lowest points? Because it's turning around in its path, right? It was going up, when it reaches a crest, it was going up, it stops and turns around, which means its velocity has to become 0. Yes, do we agree with that? So at the extremes, its velocity is 0. At the middle, the velocity is the maximum at the central point. Okay? Now, it is possible, for example, let me try and show you this. Okay, this is a little difficult to control precisely, but let me try. Okay, can you see that the displacements of particles P and Q are the same at this point in time rather. Displacements are identical, but are the velocities identical? They're not, right? Because take a look, when I restart it, I will restart it. Look at the motion of particle P, look at the motion of particle Q. 1, 2, 3. As you can see, when I restarted it, particle P started to go upwards, but particle Q started to go downwards. So clearly the velocities are not the same. Do we agree with that? They may have the same displacement, but they have different velocities. Okay, that's the important point. Alright, now let's look at the right side graph. Okay, over here. This shows just what particle P has done over some part of the time. Alright, again they look the same, they look similar, right? But they're two different graphs. That's the point I want you to appreciate. Because the left hand side, on the x-axis you have time, on the right hand side you have distance. So they are not the same graph. They're two different graphs entirely. Alright, I just want you to appreciate that point. Now, next point. How this is one cycle. Yeah, down, all the way up and back to the starting position. So it's one cycle is having gone through all possible displacements. Okay, that's one cycle. How long has particle P taken for one cycle? Look carefully. 0.1 seconds precisely. It's taken 0.1 seconds. Okay, now does this make sense? Yeah, and so, or rather let's relate it to the parameters. We can see that it took 0.1 seconds. How do we relate it to the wave parameters? As you can see, we had set the frequency to 10. Now if you remember what we'd done in class, we had said that frequency, yeah, equals 1 by time period, or time period, time for one cycle, equals 1 by frequency, and that should be equal to 1 by 10, which is equal to 0.1. Isn't this what you got? Isn't this what you observed? So does this make logical sense that the time period should be 0.1 seconds? Okay, can you all type your names once please, so I know who is who? Okay, Bhushan, can you not see the chat box? There's a green, at the green top side there should be a chat box. Can you not see that? You need to click open, you need to open that. Okay, so now we understand these various parameters with respect, or we understand the idea of time period with respect to a transverse wave. Okay, now what more can we do? Let me just press reset, and now let me change this frequency from 10 Hertz to 20 Hertz. Okay, that's what I've done. 10 Hertz to now 20. Oops, this is really sensitive. Okay, there we are. 20 Hertz. Okay. Now, let me. I'm going to reload this. Oh, I needn't have done that. Never mind. Never mind. Okay. So this was lambda was 4 meters. This was 20 Hertz. Amplitude was 2. Position of P was 4. Position of Q was 5. To start with, phase angle, we said W is at the bottom. Now I've changed the frequency. Everything else is the same. The only thing that's different now is the frequency, which is now 20 Hertz instead of 10 Hertz. Okay? See what happens when I press start. Look at the right side graph. Okay, so now look at the frequency number that we've used here and tell me what the time period should be. Based on the calculation we just did, what should the time period be? 0.05 seconds. How do you get that? 1 divided by 20. Yeah, that's 0.05 seconds. Is that what you get here? For one full cycle, how long is it taken? 0.05 seconds. Yeah, for two full cycles it's taken 0.1 seconds, which means that each cycle is now taking 0.05 seconds. What does this cycle mean? It's basically particle P staying in its place, but basically going down, all the way up, down again. This is one cycle. Second cycle down, all the way up, down again. These are the two cycles that actually took place in this graph that we are seeing. Okay? Alright. Now, again, let me reload this page. Let me reset the parameters one more time. Okay, I'm going to set frequency back to 10 Hertz. I'm going to set the amplitude back to 4 meters. I'm sorry, not amplitude, wavelength. Amplitude is back to 2. Okay, now I'm going to again set particle P at the point 4, and I'm going to set particle Q at 0.5. which is our starting points that we started off with in the previous experiment. Okay, case 1 there. Alright, same parameters. Now how can we verify this wavelength number? We've set it to 4. Okay, what is wavelength? We can do this using the definition of wavelength. And what is that? It's really the distance between two consecutive points or two consecutive particles that are in phase. What does in phase mean? In phase means same displacement and same velocity. Okay, at any point in time, both those particles must have the same displacement and the same velocity. Okay, so what are candidates? Let's look here. So this is for point P. What's the next point in phase? It could be 0.6. It has the same displacement. It's not moving, so we can't estimate the velocity. But certainly it could be 0.6, which is also at the 0 position. It could be 0.8. It could be 0.10. Yes, do we agree? It could be any of these, but we really don't know which one until we figure out the velocities. Yes, it could be any of these three could be in phase, all right, with particle P. So now let's adjust Q till it is. So do we agree that particle P and particle Q at 5 are certainly not in phase? Can we agree with that? Because their displacements are completely different, right? So we can say that, okay, the position 4 and 5 cannot be in phase, okay, for sure. So now let me adjust particle Q so that it matches with 0.6. Can you see that particle Q now matches with 0.6 on the axis? Now we're going to try and see whether they're in the same phase or not. That's our goal. Okay? I'm going to start it and you tell me whether they're in the same phase or not just by observing what you see. Remember, phase requires that both particles, or if you say two particles are in the same phase, it requires them to have the same displacement and the same velocity at any point in time. So now you're comparing two particles, which means you're looking at the left hand side. Here we go. You tell me, are they in phase? Why are they not in phase? Should be fairly obvious. I've paused it now at a situation where their displacements are different, right? At a certain point in time, their displacements are different. Yeah, yes, the velocities are also different, but look at this, look at where I've paused this. Their position, their displacements are completely different, so you don't even have to worry about velocity. Yes, does that make sense? So we can clearly state that the particles at 4 and particle at 6 are not in the same phase. Okay, let's go a little bit further. Okay, let's play it and just observe the motion of P and Q a little bit more carefully. Can you see that particle Q is doing the exact opposite of what particle P is doing? It's the exact opposite. Yes? So really, these two particles are in opposite phase, not in the same phase. Completely opposite phase. Do we agree with that? Okay, very good. Alright. So now, clearly it means they're not in phase, and therefore particle 4 to the distance between 4 and 6 cannot represent one wavelength. So let's stop it and let's just restart the whole thing one more time. Again, I set the frequency to 10. I set lambda at 4. Control plus F will clear the graph on the right. Okay, well, I don't really care about that. I just need to get the left hand side running properly. Okay, so here we go. Particle P. Now remember, the second candidate, the first candidate was 0.6. Yes, do we agree with that? That was the first candidate to investigate. Now the second candidate really is therefore particle 8. So let me move Q till it's at particle 8. Do we agree now that Q is at particle 8, at 0.8? Now what I want, I'm going to start the experiment one more time, and I want you to now look at the motion of P and Q and tell me whether they are in phase or not. Okay, let me also move W so that it coincides with the trough as before. Yeah, I'm going to start the motion, and now please tell me whether you think they're in phase or not. Here we go. Rest of you, is it clear that they are in phase? At any point in time, their velocities and displacements are identical. Do we agree with this? Okay, so the particles are now in phase. We have discovered what is the distance between 0.4 and 0.8. 4 meters. Particle P is at 4, particle Q is at 8. What's the difference between them? They are consecutive particles in the same phase. What's the position difference between them on the x-axis? 4 meters. And can you see that that's our lambda setting? Also 4 meters. Yes? So we've verified our setting, and we've now understand, hopefully, at a very intrinsic level, what does it mean? What does wavelength mean? Okay, in a transverse wave. I hope we understand that point. Okay. Alright, so now let's calculate the speed of the wave. Okay. To do that, we are going to need both graphs. Right. Again, I'm going to simply refresh the browser. Start all over from scratch. Yeah, it's a little painful, but it is what it is. So frequency at 10, amplitude at 4, lambda at 2. I set position P to 0.4, Q to 0.6. Okay, and W I'm going to set to coincide with particle P. Okay, they overlap each other. Yes, do you agree with that? W and P overlap with each other. Okay, very good. So now what I'm going to do is I'm going to start the experiment. I'm going to try and stop it when exactly one cycle is complete. Okay, exactly one cycle. So let me start. Here we go. That's down, particle P all the way down, now going back up, all the way up to the top position, now coming down to the bottom position, there. Do we agree that the cycle time should be 0.1 seconds? Can we agree on that? And that's what the graph on the right shows. Okay, how far, so 0.1 second has passed. Okay, in all this, yes, we've slowed it down a lot, so it's not 0.1 second, it's a lot in real life. But as far as the experiment goes, 0.1 second has passed. How much has this wavefront traveled? It was at P. The front has traveled how many meters? It was at 0.4, it's now at 8. So the wave has traveled 4 meters in 0.1 seconds. Therefore, what is the velocity of the wave? Velocity equals distance by time. What do you get for velocity? Distance traveled 4 meters, time taken 0.1 seconds. What do you get? 40 meters per second. What was the formula that we discussed in class? We discussed in class that velocity of a wave equals frequency times wavelength. What's the frequency? 10. What's the wavelength? 4. Multiply the two, what do you get? 40 meters per second. And we've just verified that that is indeed the speed of the wave by just looking at its motion. Do we agree with this? Okay, so clear about the formulae, where those formulae come from and so on and so forth, and what they mean with actual particle motion. Okay, very good. Now let's re-verify this. Yeah, let me just change this now to 20 Hertz. Okay, I'm going to repeat this, and this time I'm going to again set the particle W so that it coincides with I have to reload, I'm sorry, there's no other choice. Okay, here we go. We're talking 20 Hertz this time, lambda at 4 meters, same as earlier. Amplitude is 2, point P at 4, point Q at 6, and point W to coincide with point P. Okay, this is our starting point. The only change I've made is to frequency. Now let's start again and stop with one cycle. Here we go. Okay, almost, yeah, slightly less than. Do we agree that the time period now is 0.05 seconds for one full cycle? And how much has the wavefront advanced? It's almost at 8, yeah, it should have been at 8 exactly if I'd stopped it correctly. But do we agree that it's at 0.8? So how far has the wavefront advanced in 0.05 seconds? Okay, don't jump the gun. I'm just asking how far has it moved. I'm not asking for velocity. 4 meters. How much time has it taken to move that much? It's one cycle, right? How much did one cycle take? 0.05 seconds, not 0.5. And therefore, if you use the formula velocity equals to distance by time, what do you get? 80 meters per second. If you use the formula velocity of a wave equals f lambda, what do you get? Okay, so you should get the same result, and hopefully now the origins of the formula are clear. Alright, let's start one more time. Start afresh. Again, frequency I'm going to keep at the old value, which is 10 seconds. Lambda at 4 meters. P corresponding to 0.4. Q corresponding to 0.6. And the wavelength corresponding to Q, point Q exactly. Remember, in this case we had got a value of 40 meters per second. Alright, I'm going to change the amplitude now to 3 meters, or 3 meters. Okay, as you can see, what does the amplitude do? It changes the height, the extent to which motion occurs on either side of this black line. So I'm going to change it to 3. And I'm going to press start and stop after one cycle. Here we go. All the way down, all the way up, and there, I've stopped it in one cycle. As we so how far has point W moved, the wave front? 4 meters. How much time has it taken to move that 4 meters? 0.1 seconds. Therefore, what's its velocity? What is the velocity of the wave? 40 meters per second. Isn't this the same value we had got when we'd used an amplitude value of 2? So is it clear that the speed of the wave does not depend on amplitude? Okay, that should be pretty clear, that amplitude is a parameter that is kind of different from the others. Yeah, well, it doesn't depend, it's not correlated to frequency or lambda or velocity. It's a completely independent parameter. Is this idea clear? Many students don't get this, that amplitude is a completely separate thing on its own. Okay? Alright, so that's transverse waves. We're now going to do some longitudinal waves. And this is our longitudinal wave experiment. Can you see this? Rest of you, can you see this? Okay, so now this needs a little bit of explanations. So these are our parameters again. These sliders are our parameters. This is our start and reset. Now, these are the particles again in the medium, the pink points. Okay, these are all the various particles in the medium. Okay. The pink dots, as are if it's air, then they are air particles. If the medium is water, then they're water particles. If it's solid, then they're solid particles. Okay. The two vertical lines, this one, red ones, the two red vertical lines represent two particles that are in phase with each other. Therefore, this distance over here, this line, which is the distance, this horizontal red line, which is the distance between two in phase particles, should represent the wavelength. Do we agree with this? Now, the blue particles are exactly out of phase with the red particles, but the two blues are in phase with each other. And therefore the blue line which separates the this blue horizontal line, which is really measures the difference between the two blue vertical lines, or those are two particles also in the same phase, but a different phase from the red particles, exactly opposite to the red particles. That should also be wavelength. Do we agree with that? All right. Okay. So now, if we compare it, so right now nothing's happening. There's no wave, yeah? So there's really nothing much to talk about at this stage. So let's use some settings. Now, if these two are exactly out of phase, yeah, the red point and the blue point are exactly out of phase, the distance between them should be 1/2 of a wavelength, which is 1 meter in this case. Do we agree with that? At the starting point. Yeah? Assume this were a transverse wave, then we'd have got, if they were exactly opposite phase to each other, remember it was 4 and 6 in the transverse waves, the particle at point 4, particle at point 6, they were in opposite phase, and therefore the distance between them was 1/2 of the wavelength when everything was, in the case of the transverse wave. Now, we'll see whether that applies in a longitudinal wave as well. Okay, I want you to see that. Now, I am going to use these settings. I'm going to use amplitude as 0.3. I'm going to use lambda equals 2, and I'm going to use frequency equals 1. I'm going to start, and I want you to see what happens from left to right. 3, 2, 1. So we'll wait till it stabilizes. The wave should have gone through the entire medium, and then wave motion has been established. Okay, so now we've got one wave has gone through the waves has gone through the whole medium. So all the particles have now participated in making the wave go through. Look at the difference between the two red vertical lines. They are always in the same phase. Yeah, look at their motion. When the left red one is moving towards the right one is also moving towards the right, in such a manner that the distance between them always stays 2 meters. Can you see that? And that's, as you know, is the definition of wavelength. Two particles always in the same phase. That's what's happening. Now the motion of the particles here is left to right. Focus on any one particle, any one of the pink particles, and see what it's doing. Its net position is not changing, average position is not changing, but it's moving from left to right. Do we agree with that? Instead of vibrating up and down, it's vibrating left and right. Rest of you, do we agree? Okay, very good. So therefore, in a longitudinal wave, the direction of vibration is parallel to the direction of propagation of the wave itself. Okay, that's the important point. All right. Again, now take the blue lines, the blue vertical lines. They are exactly out of phase with the red particles. Okay, exactly. But the two blue points particles are also in phase with each other. And therefore, the horizontal blue line, that's the distance between the two, also stays constant at one wavelength, which is 2 meters. Do we agree with that? However, I want you to focus now on the difference between a red and a blue line that are next to each other. Okay, they're exactly opposite to each other. Can you see that the distance between them expands and contracts because they are out of phase with each other? Can you see this? Look at this as measured, say, by this first green line. Yeah, it keeps changing. Okay? And why is this happening? Because you are seeing that in some places particles are getting bunched up, and in other places they're really moving away from each other because of the nature of vibration, which is slightly delayed. This bunching up of particles is called a compression, and this particles going far away from each other is called a rarefaction. Is this clear? Clear what a compression and a rarefaction is? Okay, do you also notice that the distance between two consecutive compressions is equal to the wavelength? By definition, right? Because now, when I say now, or let me pause it, hold on. Okay, now can you see that the red line in the middle, or the red line on the extreme left and the second red line, these are the vertical red lines I'm talking about. The first and the second red lines are right in the middle of two compressions. Do we agree with that? And can you see that the distance between those red points is still 2 meters? That's equal to the wavelength of the longitudinal wave. So that should tell you that the distance between two consecutive compressions and two consecutive rarefactions equals the wavelength of the longitudinal wave. This is identical to a transverse wave, yeah, where two consecutive crests represents a wavelength, two consecutive troughs also represents a wavelength. And as you can see, the blue lines are now right in the middle of two rarefactions. Do we agree that the distance between the two rarefactions is still 2 meters, as seen by the length of this blue line? Okay. Alright, so let me just stop. Let me press reset and go back to a starting point. This time I'm going to change amplitude to 0.15 meters. Okay, halving the amplitude. Okay. I'm going to press start again. Now see what happens to the wave. Again, you can see that the wave is propagating by compressions and rarefactions, but the compressions are not so tight as earlier, and the rarefactions are not so open as earlier. Yeah, let it stabilize. It may seem like the distances are different. Let it just stabilize for a second, and once there, it's kind of stabilized on the left hand side of the medium. So you can see that the compressions aren't as tight as they were before. You had much more overlap in the previous case. Here you have less overlap. Okay, but that doesn't change the wave parameters. The distance between two in-phase particles still remains 2 meters, and the distance between two compressions or two rarefactions still remains 2 meters. It's just that the vigorousness of the compression or the rarefaction, the extent of compression and rarefaction is changing. Do we agree with this? Again, the idea that amplitude is a different parameter. It's not really connected to wavelength and frequency. It's by itself, it's a different thing. Okay, stop, reset. I'm now going to change the amplitude to 0.5 meters and see what happens now. Here we go. Can you see a lot more bunching up now? The expansion, the compression is a lot more, and the rarefaction is a lot more open as well. So the distance between two consecutive particles in a rarefaction is much more as compared to the previous case. So that's the impact of amplitude. Okay, it doesn't really change how the velocity of the wave or the frequency or the wavelength. The only thing it changes is how much of a compression it is. And that should give you a sense for why the amplitude of sound matters to the intensity or the volume of sound. Think about it. If a pressure wave hits your eardrum hard, isn't it going to hurt you? That's loud volume, right? And if it's a mild vibration, such as when we saw in the first case, it's just 0.15, your eardrum hardly vibrates, you can hardly hear it. Does this help explain how amplitude dictates the volume of sound? Okay, very good. All right. Finally, I want to do one last case. I'm going to set amplitude. Oops, what happened here? I'm going to set amplitude back to 0.3. I'm going to set lambda to 1. And I'm going to set the frequency to 5. Note what happens, yeah? Just for a flavor of what happens when you change these parameters. 3, 2, 1, here we go. Can you see that the vibrations are a lot more? These lines seem to be moving a lot faster than earlier, right? That's really what's happening when you change the frequency. They're vibrating left to right much faster than they were earlier. Okay? And the wavelength is shorter, that's all, because I reduced the lambda. So the distance between two compressions and two rarefactions has now reduced. Let me stop this. Is this clear up to this point? Any trouble up to this point? Okay, good. Now what I'm going to do finally is just look at this experiment here, and I'm hopeful that you can hear this. Yeah. So I'm going to turn this audio enabled switch on, and I want you to tell me whether you can hear this at all or not. Okay. 3, 2, 1. Can you hear the sound? Okay, so that's the sound, so I'm going to pause it. So basically what we have here is a sound source, and you can see these sound waves propagating. Note that they're all longitudinal waves in the forms of compressions, which are the black wavefronts, and the rarefactions, which are the white wavefronts. Okay, we can vary amplitude, we can vary frequency, and we can see what happens. Okay, that's our goal. Now, so first let's just play it and see what's happening. So you can see that, okay, let me just observe it for a few seconds and I'll talk. Okay, you can see therefore that it's the wavefronts as they strike the ear, yeah, they move through the medium, strike the ear, and that's how you can hear sound. Now, what I'm going to do is I'm going to start playing it, and I'm going to change the amplitude. I'm going to move it down and I'm going to move it up. And I want you to listen to what happens to the sound as I change the amplitude. Okay? Here we go. Give me one moment. Okay, so here we go. This is the bass sound. I'm now going to increase amplitude. Sorry, give me one moment. I should have set it at one level. Okay, this is our bass sound. Can you hear the sound? The bass sound? Can you hear this? Okay, I'm going to increase the amplitude and tell me what you can hear. Oops. I'm going to reduce the amplitude. Sound's gone in this case. Note that the strength of the waves is also gone. Okay, and make it a little bit higher, see what happens. Can you see this? As I change the amplitude, the strength of the wavefront changes and the volume of the sound that the listener here changes. But the volume of the sound you're listening to is changing. Yes? Do you agree with that? Let me increase the amplitude, see what happens to the wavefront and the volume of the sound. Okay, clear? How amplitude changes volume? Okay, now I'm going to change frequency. Let me bring the amplitude back to somewhere in the middle. I'm going to change frequency, okay? And look at what happens to, as I increase and decrease the frequency, look at what happens to the distance, okay, or the rate at which these wavefronts are arriving at the listener's ear. That's the first thing to look out for. Second thing to listen to is what's happening to the sound as I change the frequency. And that's the slider on top here, okay? 3, 2, 1, here we go. I'm increasing frequency. See, waves are arriving much faster. And you can hear the change in pitch of the sound, right? Now I reduce the frequency. You can see that the sound has gone down in pitch. The waves are arriving much slower as compared to earlier, at a much slower rate, but the wavelength has increased so as to keep the velocity of sound constant in the medium. Yes, can you see that? Okay, I'm going to stop this, and can you go back to the class, please? Okay, did you all listen to that? Was that clear? So do you think you understand sound a little better now? Do you understand waves a little bit better now? Okay, that's very good. I'm pleased that you do understand it better. Let me just stop the recording one moment. Oops, I'm sorry. Oh dear, I'm having trouble with this.